Physics has rules. Strict, mathematical, non-negotiable rules that govern how the universe works. These rules tell us what can exist and what can't, what's possible and what's impossible. And then we look up at the sky and find things that shouldn't be there. Not things that are rare or unusual, things that directly violate the laws of physics as we understand them. Objects that are too massive, too old, too energetic, too organized. Things that make physicists look at their equations and realize something is fundamentally wrong. Here are 10 things in space that, according to our current understanding of physics, absolutely should not exist. Starting at number 10, we have supermassive black holes in the early universe. Black holes grow by consuming matter. The bigger they get, the more they can eat, and the faster they grow. But they start small. When a massive star collapses, it creates a stellar mass black hole, maybe 10 to 100 times the mass of the Sun. From there, it has to eat its way to becoming supermassive. The problem is time. Growing a black hole from stellar mass to a billion solar masses takes billions of years. You need a steady supply of matter falling in at a certain rate. Except we've found supermassive black holes that existed when the universe was less than 1 billion years old. Quasars powered by black holes billions of times the mass of the Sun, shining in a universe that was barely out of its infancy. There simply wasn't enough time for these black holes to grow through normal feeding. Scientists have proposed that maybe they started from unusually massive seeds, or maybe they fed at rates higher than we thought possible. But every proposed solution requires special conditions we haven't confirmed. These black holes exist. We can see them. But according to standard models, they shouldn't. At number 9, we have the Methuselah star, which is older than the universe itself. The universe is 13.8 billion years old. We know this with considerable precision. Everything in the universe must be younger than 13.8 billion years. That's not a suggestion. That's a hard limit. Then there's HD 140283, nicknamed the Methuselah star. When astronomers calculated its age based on its composition and evolutionary state, they got a problem. The star appeared to be 14.5 billion years old, older than the universe. This is impossible. You can't be older than the thing you were born in. After considerable debate and refinement, astronomers revised the star's age down to about 14.5 billion years, give or take 0.8 billion years. The error bars now technically overlap with the universe's age, so the contradiction isn't quite as stark, but it's still uncomfortable. The star sits right at the edge of being impossible. The fact that we found a star this close to violating causality itself suggests something about our understanding of stellar aging or the universe's age is slightly wrong. Number 8 is the giant arc, a structure so large it violates the cosmological principle. The cosmological principle is one of the foundational assumptions of modern cosmology. It states that on large enough scales, the universe is homogeneous, the same in all directions, with no preferred locations. Matter should be distributed relatively evenly. The giant arc is a structure 3.3 billion light-years across. It's an arc-shaped arrangement of galaxies that spans a huge portion of the observable universe, and it shouldn't exist. According to the cosmological principle, structures larger than about 1.2 billion light-years shouldn't form. There hasn't been enough time since the Big Bang for gravity to organize matter into coherent structures that large. The giant arc is nearly 3 times larger than the theoretical limit. And it's not alone. We've found other massive structures that violate the same principle. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, each one too large, too organized to fit within our cosmological models. Either these structures formed through processes we don't understand, or the cosmological principle is wrong. At number 7, we have ultraluminous X-ray sources that are too bright for their mass. When matter falls into a black hole, it heats up and emits X-rays. There's a limit to how bright this emission can be, called the Eddington limit. Radiation pressure from the X-rays pushes against infalling matter. If the emission gets too bright, the radiation blows away the infalling matter, choking off the process. The Eddington limit gives you a maximum brightness based on the black hole's mass. A black hole of a given mass can only shine so brightly. This is physics. This is non-negotiable. Ultraluminous X-ray sources violate this limit. These are objects shining with X-ray luminosities that exceed the Eddington limit for stellar mass black holes by factors of 10 or more. They're too bright for what they appear to be. Scientists have proposed that maybe these are intermediate mass black holes, or maybe the geometry of the accretion flow is different than we assume, but these are all patches on a problem. Ultraluminous X-ray sources are doing something they shouldn't be able to do. Number 6 is WT1190F, the mystery object that fell to Earth and shouldn't have been there. In 2015, astronomers detected an object on a collision course with Earth. It was small, only a couple meters across, and it was going to impact in the Indian Ocean. But when they traced its orbit backward, they found something weird. WT1190F wasn't following a normal orbit. It was on a highly elliptical trajectory that took it far beyond the Moon, looping out into deep space before coming back. And its density was too low. It was either hollow or made of something extremely lightweight. The leading explanation is that it was space junk, maybe a rocket stage from an old lunar mission. But nobody could definitively identify what mission it came from. It entered the atmosphere and burned up over the ocean. Here's why it shouldn't exist. We track space junk. We catalog everything humans have launched. WT1190F was on an orbit that should have been recorded, and it had physical properties that didn't match any known debris. Either it was a natural object with an impossibly weird orbit, or it was human-made debris we somehow completely failed to track. At number 5, we have regular soft gamma repeater emissions that pulse like a clock. Soft gamma repeaters are neutron stars with extremely powerful magnetic fields that occasionally emit bursts of gamma rays. These bursts are energetic, violent, and typically irregular. Stars don't keep time. Magnetic field reconfigurations are chaotic, random processes. Except some soft gamma repeaters pulse with startling regularity. SGR 1935 + 2154 has exhibited periodic bursts with timing precision that rivals atomic clocks. Other sources show similar behavior, emitting pulses at intervals so regular you could set your watch by them. Natural astrophysical processes don't do this. Earthquakes don't happen on a schedule. Volcanoes don't erupt at precise intervals. Magnetic reconnection events should be chaotic, driven by turbulence and instability. The regularity suggests something mechanical, something structured. Scientists have proposed models involving neutron star oscillations or orbital dynamics in binary systems. But many of these repeaters aren't in binary systems, and the precision exceeds what most natural oscillation models predict. The universe is beaming regular, timed pulses of gamma radiation at us, and we can't fully explain why they're so regular. At number 4, we have perfectly spherical stars that shouldn't be able to form. Stars rotate. When they form from collapsing gas clouds, conservation of angular momentum means they start spinning. The faster they spin, the more oblate they become, flattened at the poles, bulging at the equator. This is basic physics. Then, astronomers found Kepler 11145123, a star that is perfectly spherical. Not nearly spherical. Perfectly spherical to within measurement precision. The difference between its polar and equatorial diameters is less than 3 kilometers out of a radius of 1.5 million kilometers. This star is rotating. It has to be. Everything rotates. But it's rotating so slowly that it's maintained an almost perfect spherical shape. The problem is that stars with this mass and age shouldn't rotate that slowly. Stellar evolution models predict stars lose angular momentum over time through stellar winds, but Kepler 11145123 has lost more angular momentum than models predict is possible. Something has slowed this star down to the point where it defies the shape we expect stars to have. We don't know what. At number 3, we have Saturn's moon Enceladus, which is far too geologically active. Small moons shouldn't be geologically active. Geological activity requires heat, and heat comes from either radioactive decay or tidal heating from a nearby massive body. Enceladus is tiny, only 500 kilometers across. It should have frozen solid billions of years ago. Instead, Enceladus has active geysers shooting water ice and organic molecules into space from its south pole. It has a subsurface ocean of liquid water. It has ongoing geological processes that require substantial internal heat, and we can't fully explain where that heat is coming from. Tidal heating from Saturn is the leading explanation. As Enceladus orbits, Saturn's gravity squeezes and stretches it, generating friction and heat. But when you run the numbers, tidal heating alone shouldn't be enough to keep Enceladus this active. The orbit isn't eccentric enough. The tidal forces aren't strong enough. Some models propose that Enceladus's core is more porous than expected, allowing tidal flexing to generate more heat. But these are adjustments to make the math work, not confirmed physical mechanisms. Enceladus is doing something small moons shouldn't be able to do. At number 2, we have the cold spot in the cosmic microwave background's impossible temperature. The cosmic microwave background is the afterglow of the Big Bang. It's nearly uniform across the sky, with tiny temperature variations of about 1 part in 100,000. These variations are well understood and predicted by cosmological models. Except for the cold spot, a region about 1.8 billion light-years across where the temperature is significantly colder than anywhere else. Cold enough that the probability of it occurring naturally is less than 1 in several thousand. Scientists initially thought it might be a supervoid, an unusually empty region of space. But surveys found the void isn't empty enough. Then they proposed cosmic strings, exotic topological defects from the early universe. But we've never seen cosmic strings anywhere else. The most radical explanation is that it's evidence of a collision between our universe and another universe during the inflationary period of the Big Bang. A multiverse collision would leave exactly this kind of signature. But this explanation is speculative, untestable, and requires accepting that parallel universes exist and can interact. The cold spot exists. Multiple independent observations confirm it, but according to standard cosmology, it shouldn't be there. And finally, at number 1, we have fast radio bursts that are too bright and too brief to be natural. Fast radio bursts are millisecond-long pulses of radio waves coming from distant galaxies. In that brief flash, they release as much energy as the sun produces in days, and some of them repeat with such regularity that they appear almost artificial. Here's the problem. Nothing we know of can produce that much energy in that short a time in such a concentrated radio frequency band. Supernovas? Too slow? Pulsars? Not energetic enough. Magnetar flares? Wrong energy signature. FRB 121102 repeats every 157 days like clockwork. FRB 180916 repeats on a 16-day cycle. Natural astrophysical processes don't keep schedules. Chaos theory, turbulence, and randomness should dominate. Regular periodicity suggests mechanical processes, orbital dynamics, or something structured. Scientists have built models involving rotating neutron stars in binary systems, precessing magnetars, and exotic emission mechanisms. But every model requires fine-tuning multiple parameters to match observations. The fact that we keep finding new fast radio bursts with different properties suggests we're not dealing with one phenomenon, but possibly several. The universe is sending us extremely powerful, extremely brief, sometimes regular radio pulses from billions of light-years away. And the most honest answer to what's causing them is, we don't know. They shouldn't exist according to any straightforward astrophysical model, but they do. 10 things that physics says shouldn't exist, and yet every single one of them is real, observed, measured, and confirmed. We didn't make them up. We didn't misinterpret the data. They're out there, violating the rules we thought were inviolable. This is what makes science thrilling. Every impossible object is a clue that we're missing something. Some new principle, some overlooked mechanism, some deeper truth about how reality actually works. The universe isn't breaking its own rules. We just haven't learned all the rules yet. If you want to see more of the universe's rule-breaking behavior, hit that subscribe button and turn on notifications so you never miss an upload.